For decades, artificial intelligence research was constrained by a very specific biological bottleneck: us, humans acting as meat computers, typing out lines of code, eventually needing to stop, eat, and sleep. But the frontier of AI research has moved into the cloud. It is now driven by autonomous swarms of AI agents, operating across massive arrays of NVIDIA GPUs, specialized hardware processors built for highly efficient parallel computing. By handing the keyboard over to the AI, the speed limit of human typing disappears entirely. There are no more weekly group meetings to synchronize progress, just continuous, unrelenting iteration. This is the premise of a protocol called Autoresearch. It removes the human from the iterative coding loop completely. You no longer build the neural network yourself. You build the agent that builds the network. The result is a codebase that can reach its 10,000th generation in a single night. It becomes a self-modifying binary, optimizing itself in the dark while the researchers rest. Running this autonomous system requires surprisingly little infrastructure: a single modern GPU, like an H100, Python version 3.1, and a package manager called UV. The entire repository is stripped down to a strict constraint of just 3 core files. The first is prepare.py. This file contains fixed constants and data preparations allowed to touch it. As the human researcher, your territory is strictly confined to the second file, program.md. This is a lightweight Markdown file where you write the baseline instructions and context for your AI agent. The final file, train.py, is surrendered completely to the machine. The agent has full authority to mutate, test, and rewrite this training script at will. Isolating the human entirely to plain text Markdown files ensures that human intent is translated directly into machine evolution, bypassing the risk of manual coding errors entirely. When the human logs off for the night, the agent activates. It opens train.py and begins its work. The agent is bound by a strict, uncompromising rule. Every time it modifies the architecture, it runs a training cycle that lasts exactly 5 minutes on the clock. Its decisions are dictated by a single mathematical metric known as val-BPB, or validation bits per byte. This measures how effectively the model compresses and predicts the data it processes. At the end of the 5-minute test, the outcome is binary. If the validation bits per byte score drops, the agent permanently keeps the new code. If the score goes up, it discards the mutation entirely. This cycle repeats relentlessly, iterating dozens of times in the dark. Because the time budget is absolutely fixed, every single architectural change is compared fairly against the others. This ruthless, automated Darwinism strips away anything unnecessary, ensuring only the absolute most hyper-efficient logic survives the night. Inside train.py, the agent actively manipulates core structural variables. It frequently focuses on the model's architectural depth, which is the number of sequential processing layers inside the neural network. Increasing or decreasing these layers changes how much complex logic the model can process, directly impacting how fast the validation loss drops within the time limit. The agent balances this against the total batch size. This controls the sheer volume of data the system attempts to process in every single forward and backward pass. The AI must find the exact mathematical equilibrium. It balances the depth of the model against the total batch size to maximize the amount of learning it can squeeze into about 5-minute window. By the time the sun comes up, the agent has executed approximately 100 consecutive, perfectly measured experiments. The resulting binary code is so densely layered and hyper-optimized that it may no longer be fully comprehensible to the human who provided the initial instructions. In the morning, the researcher simply wakes up, reviews the overnight log of successful experiments, and deploys the vastly improved model. While the baseline system is designed around a powerful H100 GPU, this autonomous research loop can actually be modified to run on smaller computing platforms, directly from a standard laptop. The first hardware hack for laptops is switching the training material to a narrow, low-entropy dataset. A popular choice is Tiny Stories, a collection of simple narratives generated by GPT-4. Next, the researcher must drastically lower the hyperparameters, the overarching configuration settings that control the training process. This means shrinking the vocabulary size and dropping the sequence limit down to 256 tokens. The model complexity also has to be reduced, dropping the architectural depth from 8 down to 4, and severely restricting the total batch size. These mathematical sacrifices shrink the computing footprint, allowing anyone to run a localized, iterating AI research swarm right from their desk. This workflow changes the day-to-day role of the AI researcher. The human is no longer a programmer. They are a governor, orchestrating a swarm of autonomous digital workers. Human effort now shifts entirely to refining the instructions inside the program.md file, carefully optimizing the overarching rules of the research rather than manually typing the logic. The trajectory points directly from a single overnight agent to massive, multi-agent autonomous research organizations with highly specialized roles. As manual coding takes a back seat, human focus moves toward the high-level task of programming the program itself.
Please like, share, and subscribe.